It's time for another episode of Extreme Makeover, NGSS edition. This time we're going to be doing an elementary school lesson about modeling coronavirus. I'm going to try and show you how we might teach this in a fully online environment, which is kind of appropriate for what most people are experiencing at this moment. I want to start with the old school way of doing this, where my teacher that I was working with said we already did coronavirus. And what she meant by that was they watched a Brainpop. And Brainpop is a wonderful tool, and it's got a lot of interesting things that are very engaging and entertaining, but it's not really doing science in terms of NGSS. You can see this screenshot that I have, and a good portion of this Brainpop lesson is a person sitting there and talking to the kids and actually talking to a robot. That's not the type of discovery and application of the science and engineering practices that we're looking for. So we need to figure out a way to do that, and how to do that when our kids are all dispersed and in an online environment. So I'm going to have you go ahead and quickly gather these materials. You need a pen, paper and pencil, a few pieces of tape, it doesn't matter which type, a pepper shaker, and if you've got an adult present, a candle and some matches. So go ahead and gather those and come back. We're going to start with a little bit of a drawing in our science notebooks. I've got this picture here of a teacher teaching some class. I want you to draw arrows to show different ways that students could get coronavirus from another person. And of course, when we're doing things in our journals, I've got this beautiful picture here, and since if you're doing it on paper, you don't have that beautiful picture, and it will take you a very long time to reproduce that. So why don't you just go ahead and draw 3 stick figures, just like I've drawn. One big one, that's the teacher holding a piece of paper, and some students. And then pause the video and try and see if you can draw little arrows indicating how coronavirus could move from one person to the next and infect them. Here's one piece of paper, or one model where the teacher gives the piece of paper to the student, and that piece of paper has touched the teacher, and maybe if the teacher is infected, that could then transfer the infection to the student. But how exactly does the virus stick to the paper? Well, we're going to do a quick investigation to try and just see what happens. So, looking closely at that piece of paper. So, what I'd like you to do is to get out your pepper shaker and sprinkle some pepper on your paper. And then carefully lift it up and tilt it so that the pepper starts sliding off. And one of the things you're going to see is that actually not all of it slides off. Some of the pieces stay stuck to the paper. And I find that a little bit unexpected, but it's something that's totally happens. Now, how do things differ if you sprinkle that paper on a piece of tape instead? You can also try and simulate what happens when you transfer from one piece of tape to another. So sprinkle on a piece of tape and then take another piece of tape, push it up against that first piece, pull them apart, and see if any of the pepper transfers from one surface to the next. And you start noticing that different tapes and different surfaces keep that pepper attached to it at different rates. The amount of pepper that sticks depends on the material. And at this point, here in elementary school, I'm just going to say, I wonder how that works. That's amazing. And we really aren't going to go into that until students learn a lot more about what materials are made out of at the atomic level and intermolecular interactions that they're going to have. And that's all happening literally in the high school level. So stay tuned, kids. You're going to have to learn a little bit more. But right now, we just discovered this exciting phenomenon, this mystery that we notice that will keep with us for years to come, that pepper can stick to paper, even though paper is not something that's very sticky, at least in our heads. So, of course, coronavirus is representing, the pepper is representing coronavirus. And as we move it from one surface to the next, it can get stuck and to be transferred. So the next thing that we're told about coronavirus is we have to be careful not to touch our face. And I wonder, why is that we aren't supposed to touch our face? What's going on there? And so we're going to think about that in a little bit more detail. And we're going to think about our face as part of our body. And our body is part of a bigger body system. And you can see this key word here, system. So I want to sort of draw our attention to some things that are properties of a system that we want to talk about. And the first one is that a system has a boundary. And if you think about us as a system, our body, it has a boundary. All the way around the edges, it's got our skin. But of course, a system wouldn't be very interesting if it was just its boundaries, like a person who is just that outline. You've got stuff inside of you. You've got parts like the blood, muscles. You've got organs like your heart, stomach, and lungs. There's so many different parts inside your body. Um, and each of those make up the parts of your system. And then lastly, we've got things that come into our system and go out of our system. There's food, there's air that we take in, we give off heat, and we give off that bathroom stuff. And so all of these things together really help make us work. In fact, it's the combination of all of these things working together that really determines our overall system properties. In this case, our health. And if something goes wrong with one of those, like let's say we don't eat the right types of food, then our health gets affected. Let's say that something's not working right, like one of our organs stops working, then our health is affected. Or imagine if we didn't have our skin and if we didn't have our boundary to keep the outside world out, well, that would affect our health too. And in fact, our skin is one of the key lines of defense we have against coronavirus. The virus wants to get inside our body so that it can start affecting and using and taking advantage of the parts that we have and taking advantage of the food that we feed ourselves. It wants to get in there, but our skin keeps it out. And wow, skin is like armor protecting us from a virus coming into our body. And I wonder how it does that. And that's something that we might be able to discuss in the middle school level. Or we could spend some time investigating it here at the elementary level, really looking and digging in at some microscopic views of skin and trying to understand how it is that skin acts as armor. But right now, I'm content just leaving it with, wow, I wonder how the skin works so effectively doing that. And this is where your face becomes important because your face, of course, has lots of holes that allow the virus to come in. You've got your eyes that have those tear ducts and stuff can come out. That means stuff can get back in. There's, of course, your nose. Lots of viruses like to make their way up there. And last but not least, your mouth. And like my little daughter is doing here, when she brings her hands into her mouth, she is taking all the things from the outside world and giving them special delivery into the inside, where they can do all the things that viruses like to do once they get inside your body, which basically means they make you sick. Let's go back to our original model we were drawing, where we were trying to show how coronavirus could get from one person to another. There's another way that we can have things transfer, and that's the most direct way. When a person breathes out, maybe that virus can get all the way into another person's face, and they can breathe it in, and that virus will get inside their body. So how exactly does that work? Well, for this, let's get an adult in the room to light a candle on the other side of the room and then blow it out. There's going to be some whiffs of smoke that we can watch, and we can watch as those spread out. Those are little particles of smoke, and in our model, this is a physical model, we're using those little particles of smoke to represent little particles of virus, and we can watch them spread out. And as you start on the other side of the room and walk towards that candle and that smoke, as you get closer, at some point, you'll start smelling it. That means that those little smoke particles have traveled all the way from the candle over to where you are and gotten into your nose. Imagine if that was a virus. And that's exactly where this rule is, that we're supposed to keep about 6 feet away from other people. Because the tiny particles of spit that we sort of give off when we're talking, they can carry viruses when we breathe out, and they usually fall to the ground after traveling a few feet. And 6 feet seems like a good safe distance where we aren't smelling things. You can test that out with your candle and see how far away you have to be from your candle before you stop smelling it. Now, of course, right now, many schools around the country are closed, and we don't have a classroom that looks like this. In fact, the classroom's empty because we are all separated. And I want to know why it is that we're doing that. How does this help us? And so we're going to investigate that right now. To do that, we're going to use a little simulation. Now, this is a simulation that my children and I coded up in the program called Tynker, and we're going to go ahead and use it. And let's start with this very first example where we have a village filled with 10 people, and I'm going to push go, and we're going to watch them move. Now, one of the people in our village is infected with the coronavirus. That's shown by this little virus, and this is a zoomed-in microscopic view of what the virus looks like that we made as big as a person's head. And here we have people moving around our village and bumping into each other. So what's realistic about this situation and what's unrealistic? Well, obviously, people have bodies and they don't float around and bounce off each other like this. But let's use that as sort of a pretend way to talk about how we just interact in our world and move around and occasionally talk with people and come within 6 feet, exchange papers with them, all of those things. Um, but the other big thing that I think that as we start talking about this, and if we were in an online chat, I'd have you type in the chat window what you think is accurate and what you think is unrealistic about this. And the biggest thing we need to address is the fact that that person who's sick there is bouncing around, but nobody else is getting sick. And that's not how coronavirus works. It spreads very easily and infects other people. So we need to figure out how to make that happen. To do that, we've put together the Coronavirus Epidemic Simulator, and you can access it here at this URL here. And I would paste that into the chat window, and I'd ask our students to each go ahead and start running it. And we want to start with a simulation with just 10 people in our village. So let's go ahead and take a look at that. We'll open up the coronavirus simulator here, and I'll make it full screen. And I'm going to hit play. And it starts with a little bit of introductory message. You start with one sick person. As other people interact with that person, they get sick because the disease spreads. So the next question is, how many people are in your village? And I said we're going to start with 10 people. So I hit enter. And let's watch them. Ooh, now when they interact with a sick person, they get sick too. And over time, it took 9.56 days for everyone in my village to get sick. Let's try and do that again, full screen here. Do it with 10 people again. And see if we get the same answer. Now, this is a random little simulator where things move around randomly, so it's going to be a little bit different every time. But we're going to look for trends. And this time it took 10.3 days. Sometimes it's going to be even longer. Those were pretty similar to each other. And what we do here now is I'd have every child in the class run the simulator and then type in the chat window what their result was. And when they do, we'll go ahead and collect those results in a table that looks like this, where we have a whole bunch of children's contributions, and we're going to record that for our 10 people. And here are some results. You can see that they differ dramatically from as high as 20 seconds to as low as 7 seconds, but my computer can automatically take the average of those, and it tells me that it's about 12.3 seconds on average, or excuse me, days. As it's 12.3 seconds in our simulator. We represent that as 12.3 days in the in real life. So that's really interesting. But our first simulation had just 10 people. What do you expect to happen in a village with 20 people? And I'd pop up a poll in our online simulator. Do you think that the disease is going to spread faster? Like it's going to take less time for 20 people to get sick than it did for the 10 people? Or do you think the disease is going to spread slower? Like it's going to take more time for all 20 people to get sick? Or do you think that there's some crazy things going on and it's going to be the same? So I'd have students answer that poll question, and then I'm going to send them out to breakout rooms where they're going to discuss this with their partner and try and discuss why they think each of these answers might be correct. And they can do that through the chat or through their video chat conference. And with Zoom, at least, I can make up to 50 different breakout rooms. So if I have a classroom filled with 30 children, I can set up 15 breakout rooms and have them each working in pairs, or I can do them in quads, or whatever works out for the groupings that I think is going to work most effectively for these kids. And then, of course, we can actually run that simulation. So let's go ahead and let's watch it together. We hit the play button here. And this time I'm going to do it with 20 people. And we'll see what happens. And it's going, and oh wow, it seems like things are spreading rather rapidly, and it only took 6.8 seconds this time. We'll do another trial, or we'll have all of our children in the classroom doing trials so that we can get lots and lots of data very quickly with 20 people here. And we'll see if it consistently is going faster. Look at that, and boom, 8 days. So when I switch back over to my data table, I can now collect a number of different trials, and here's some that I did, and I found that the average for 10 people was 12 days, and the average for 8 people the average of 20 people was less, was just 8 days. And so we're starting to see this trend. And we can start trying to graph that trend on a graph that looks like this. If we have the number of people in our village from 3 to 50, and the days until everyone is sick on the vertical axis from 0 to 40. So let's start by doing what I always like to do when we look at a new graph, which is label the axis with some words. So if there's only 3 people in a whole village, I call that a nearly empty village. At the other end of this graph here, when there's 50 people in a village, what are we going to call that? We can ask our students to chime in, or I can just show them. That's a crowded village. Now let's say that it only takes like 1 day for everybody to get sick. What does that mean in words? That means that the disease spreads really quickly. But if it takes 40 days until everyone in the whole village gets sick, that means that the disease is spreading more slowly and it takes longer to spread. So now that we have this graph, let's try and think about what this graph is going to look like when we actually start plotting our data. We know that we've done simulations at 10 people and at 20 people. And we found that when there were 10 people in the village, that it took about 12 seconds. And then when there were 20 people, it took less time. It took only 8 seconds. And so then we can start extrapolating out and trying to see how long will it take with 50 seconds. And we can ask our students to make predictions based upon what we know here. Is it going to be 10, 5? How many seconds do they think it's going to be based upon what the graph looks like right now? And then we can actually run that. We can do the same thing with if there's only 3 people. What's the graph going to look like? Is it going to be 20 seconds? And then once we do that, we collect the data from all of the students, and we get a graph that looks something like this. And this is really important for us to see, is that when we are all crowded together, the virus spreads really quickly. But when we separate apart and make it so that we don't have as many people around us, we can make that virus spread out so that it takes a lot longer to spread, and that means that we can hopefully stem off a lot of the problems that happen when we all get sick at once. And so that's one of the reasons why we're all sitting where we are. But of course, this is not quite accurate about the way that things are working here. What happens if we modify the code so that all the non-infected people stay at home in one place, just like we do, like we're doing? We can go ahead and do that. I'll go back over to my coding here. And I have to find these different actors on the right side. Here I've got the infected people, and there's a code for that, and then the not infected people. And you'll see in my code that there's a spot here where it says, to make people stay in one place, set static is a word that basically means not changing, to true. So allow them to roam, we're not going to be static, but this time we want them to be static. And so let's go ahead and see what happens when we do that. Let's make this full screen. Let's make this go away here. And we'll run this. And we'll do 10 people again, just like we did before. And last time it took about 12 days for 10 people to get all contaminated here. This time we'll watch here now. You can see that people still get sick, but now they don't move around. They don't spread the sickness as they're moving. And so we'll see how long it takes until all these people here, who are not interacting nearly as much because they're all at home in one place. Maybe they go out occasionally to the grocery store, and so maybe they do interact with a sick person every now and then, and so we might still have the sickness happening. And you can see I'm talking for a long time, and I still have people that haven't gotten sick yet. And this is really slowing down the spread of the disease by keeping people in one place. Let's speed it up. Wow, it took 91 days for everyone in our village to get sick. I had to speed up the simulation to show it in the video. So when we put a number like that on our graph, it doesn't even fit. Remember before, it took about 12 days for everyone in our village to get sick when we had 10 people in the village and they were moving around. But we were able to slow that down to 90 days when we had people staying in one place. We want to see if students really are putting things together and understanding what's going on. So we're going to ask them to construct an explanation. We want them to really answer the question, why do we have to stay home from school this whole time and not visit with other people? We're going to prompt them to provide evidence from the simulator. We're going to have them type their responses into the chat window so that everybody can see all the different ideas. We can have them work in breakout rooms to develop this if they need some scaffolding. We can have them type it as an exit ticket. But this is our opportunity to really see what happens. And then at the end, we'll be able to look at that as an artifact and really try and construct what facts did the students get, what ideas did they get, are they putting together the cross-cutting concepts here about stability and change, and we can go from here so that when we meet next time, we can come back together and work on something that's not coronavirus related. So in my example, the next time that I'm going to have them going to notice the nature around us, and we'll do an online experience where we're going on a scavenger hunt and bringing things together, because each one of us only has a tiny little piece of nature that we might have access to going out on the street, maybe going into our backyard if we have one. But when we all put it all together and bring it together on Zoom, that might be our next opportunity for learning. So thanks so much for joining me, and I hope that you have a wonderful time in your self-quarantine and help your students experience a wonderful example of science doing it together.